Good morning and welcome. This is John Barnes. I'm the Technical Manager of EngineSoft UK. This is the second part of a four-part series looking at some of the capabilities inside modeFRONTIER. And this week we're going to be looking at response surfaces and looking at how to speed up your optimization through using those. So the plan for today is for us to... One second. First of all, have a introduction to modeFRONTIER, briefly introduce a case study, and then hopefully spend the majority of the time demonstrating the capability inside modeFRONTIER. And then there's the opportunity for you to ask some questions. Just punch in the questions into your text bar at the bottom of your GoToWebinar session, and I'll be happy to answer any questions at the end. What is modeFRONTIER? Straightforward, it is an MDO tool, a multidisciplinary optimization tool. If you are trying to optimize your design, typically you might have a base you've come up with, you've got it already modeled in CAE, or you've got some test bed somewhere. Typically the way in which we work is that we have different disciplines, different engineers doing those analyses. Somebody manages to optimize one part of the design, but often that's a detriment to other disciplines that people are for. We don't necessarily meet all of the targets that we wish to. When we're talking about MDO, we're trying to push all of those together to work as a team. We may not get in one location the true optimal, but as an overall, we're trying to push all of our objectives to their limit. And the key thing that enables us to do this is typically integration, automation, and exploration. So what is integration and automation? Typically you have some decisions, you've got your product or process that again could be CAE or some kind of test bed, and then you're looking at the performance coming out of that. Typically there's an engineer in the loop trying to make an understanding about the relationships between their inputs and their outputs. That can be quite difficult depending upon the number of parameters and keeping a track of all the interaction effects. So what we're looking at is putting some smart algorithms to drive that design and to automate and integrate that process. Now modeFRONTIER is there to be able to do that, and that places the engineer outside in a much better position to look over the entire process rather than looking at designs on a sort of a run-by-run basis. But today what we're looking at is that product or process could take hours to run. Certain algorithms may not be suitable for this kind of optimization just because of time. So what we're going to look at is surrogate models or response surfaces, how we can replace part of this process by just sampling a part of the design space and training these response surfaces that we can then run an algorithm over the top to view the design space and try optimal in seconds rather than in hours, and really reduce the time that we're taking to do this kind of work. So what is an RSM? It's just a numerical model that approximates the behavior of a system. It typically starts with design of experiments, some sample points. Now there could be a number of different ways you could draw a line through those points. Typically there are two methods. One is an interpolation method, and the other is an approximation method. There are a number of different methods that are available to do that, and you could probably draw a line through those points in multiple ways. But then once you've drawn those response surfaces through, we can then validate them and establish how good their quality is and how predictive they can be. So what we typically use is another design of experiments called a validation set to be able to validate them. Now this is really important. If we were to validate using the original training points, then certainly for the interpolation methods there would always be a perfect match. So we always use a validation method or set to be able to do this validation, and then we can get a good comparison between the different methods. Okay, so that's modeFRONTIER, just setting up the response surfaces. This is the particular problem we're going to look at. This is also related to the hardening of steel and the carburization and nitriding process. Just that you're aware, this is just a process where you add a layer of carbon or nitrogen to the surface of some low carbon steel. It goes under some form of process, and then you get a different coat on the top that would increase the hardness of the product that you're looking at. The data that we're looking at today are physical samples and have been stored inside a spreadsheet. So in terms of the experimental process, kind of mapping back over the diagram that I've shown before, there were about 25 different parameters that could have been tuned. It was plugged into this carburizing process, and then there are about 4 outputs that we're looking at. Now, what we're going to do today is going to be a subset of those, and I'll show you how you would filter out some of those parameters. But rather than plugging them through an algorithm, we're going to first of all sample the design space. So we've got 596 experiments. We're then going to train the response surface over that set of data, and then once we've got that response surface, then perform a very fast optimization over the top of that response surface. The objective is really to maximize the hardness. We can have different hardness at different depths of product, and we're going to take a single depth and we're going to try and take that and optimize that value of hardness. So the typical steps of doing this work is first of all to import that data from Excel. We're not going to do this time, but we can tidy up that data. We can look at outliers and remove errant designs. We could perhaps look at some of the sensitivity analysis. This is what we described in our last webinar. But what we're going to show this week is really, first of all, how do you train the response surface? How do you validate the response surface? And then how do you then go and plug that in to run another optimization? So I want to go straight now into the demonstration. If I go to modeFRONTIER, and so the first thing that I want to show you is how to open up Excel and get modeFRONTIER to read data very quickly in, and not only just read it into a table of data, but also to generate on the modeFRONTIER workflow the workflow that describes that data. So the way that we do this is using the data wizard, and we can import data from either a database or a file. In this case, it's going to be an Excel file. I have it already stored in this spreadsheet, so I open that up. It will give me some information about that spreadsheet, about its size, its name. I can even view the data as it is stored inside that spreadsheet. Notice that certain rows might need to be tidied up, or certain columns may be blank. But we can use this to tidy up our data. So notice everything's grey at the moment, and I can remove a particular row. Maybe I don't want a duplication of 2 ID columns, don't want that column there. I can scroll across and notice that this column here is blank. I can remove that column, and then once I've removed that column, then everything appears to have become white because I've got no more errors in those cells. But even down here, I've got some data that's slightly corrupted, and there's more things. Now there are some parameters that I don't want, so we're not going to take all of these columns of data. So I just happen to know which ones I'm not interested in. So I'm not interested in these final columns. I'm not interested in some of these standard parameters that make up the composition of the steel. So I can remove those, and then that can leave me with hopefully a column of ID, 5 input parameters, and 1 single output parameter. I can extract the variable names from the first row, or if there was a different row, I could change the row number, and I can also extract the run IDs from a particular column. Once I've done that, I can click Next, and then it shows me the data that I'm interested in. Then I can go and select these 5 columns, and I can associate them to an input inside modeFRONTIER, and I can select the other one to be associated to an output. I click on Next, I can even apply objectives if I want to, so I could add an objective to my output. I can apply a user expression like you typically can inside modeFRONTIER, and I could just make an expression of the C profile. So that's the amount of carbon that is on the part that we're carburizing. So we can also change the name, just say that we want to maximize C, and we can change the type to make sure that we're maximizing that value. Now once I've done that, I click next. If I wanted to add a constraint, which I don't in this case, I could do in a very similar process to add a constraint. I could click next. I'm given a summary at the end, but I'm going to click finish, and what I want you to notice is that modeFRONTIER has now generated a workflow that represents all of that data that was inside that Excel spreadsheet that I was interested in. And it's all very quick and ready to run. Even the inputs themselves, it's also given me the upper and lower bounds ready to run an optimization that would be valid for this case. Now the first thing I want to do is this steel ID. It's not really a true variable, it's just the ID of the steel, so I could make that a constant and just set it to a constant value of 1. So once that's important, we've got a workflow there. In the design space, we have an equivalent data table that has all of the data that was inside that Excel spreadsheet, and that's ready for us to do some post-processing. So I can quite quickly start plotting any chart on this data. So if I wanted to run a parallel coordinates chart, I could, and I could start to interrogate my designs. And I could see the relation of max C to depth, knowing that with a high depth I'm going to get low values of max C, and then as I decrease the depth I get higher values of max C. So I could probably already assume that I'd probably want low values of depth anyway if I'm going to be optimizing. In that case I could also plot a scatter chart and just look at my 3 other input variables and actually just see the design space. So this is the design space in terms of my inputs, and notice that the data that was generated is quite uniformly distributed around the design space. So let's get on to training some response surfaces. This can be done instantaneously using the response surface methodology tool. There are 2 methods. There's a RSM manual and RSM automatic. In the automatic mode, a lot of the advanced parameters are sort of hidden, and you just use the standard values. If you want to do things in more detail, you can use the manual method. But in this case, I'm just going to use the RSM automatic method, just to show you how quick it can be to set this up. So what we're presented with is just a single page wizard to be able to work through. So I select the design table that I want to train the response surface over. I can select my inputs and outputs. In this case, I don't want steel ID to be part of my response surface. It's not really a true variable in that sense. And then I've got a number of different regression methods that I could try. So I could use a polynomial SVD with a polynomial degree 1. Maybe I'll try a stepwise regression which would step through polynomials of a number of different orders, and it would find the best one. Maybe I want to try a Kriging method or a radial basis function, or maybe I could select them all. Now I can also get it to automatically validate. So I could enable the RSM validation, and if you're familiar with response surfaces, there's a number of criteria to establish whether or not the regression method is better than another, and typically we can use an R² value, which needs to be close to 1. As I mentioned before, we need to split the data so that it trains it on a training set and then validates it against a validation set. So I can automatically say I want to keep, let's say, 2% of my designs purely for validation, and it would automatically split this design table up into 2 tables, and then I can tell it to add those 2 tables back into modeFRONTIER so I can see how it's been split. Now once all that is set up, I can click next. modeFRONTIER will go away and it will train those response surfaces in a pretty quick time. So now that's done, I can click finish. I'll go back to my desktop. First thing to notice is that I've trained the response over this design table, and now it's generated two subtables, one showing this is the data that the response surfaces have been trained over, and this table I should use for validation, so 16 designs to validate against. And then we also have down here 4 of those response surfaces ready for me to interrogate. Excuse me. Now, if I wanted to look at the coefficients, let's say, of the polynomial SVD, I could go into the summaries and logs and have a view of how they've been trained, and it will give me a summary of the coefficients. So notice that that's of degree 1. It will give me a summary of the quality of the training as well, and how well they lie over the bottom, and it gives you a number of different reporting features. Now if I was to click on the stepwise, it runs through a number of different polynomial degrees. Then I can see which order it's actually managed to train it to. So it's to the squared order. So there's a lot of data that could be transferred back, just looking at some of these reports, but the best way is probably to select all of those response surfaces and use this RSM evaluation chart. Now in this case I have to make sure that I'm always validating using my validation set, so it will give me the correct values. And then it gives me this really powerful table at the top which ranks those 4 response surfaces. So R squared has to be close to 1, so I can rank them. So I can see that the stepwise regression has the closest value to 1, and modeFRONTIER quite nicely colours in green the ones that are the best. So pretty much across all of these 5 values, that stepwise regression comes out on top. So we've got our absolute error, our percentage relative error, our normalized error, R squared, and then some relative value that the lower the value, the better it is. So on all 5, we can see that stepwise regression is better, and we can see some of the difference. So if you look at the SVD, you can see that this is a linear fit of the response space, but if we look at the stepwise regression, it's non-linear for CRBT. Now if we were to look at some of the scatter charts, you can see how that data has been trained through those points, and how that is probably a better fit than the way in which the polynomial of degree 1 has. If we start looking at the Kriging or the radial basis function, then it becomes very non-linear and it becomes a very poor fit through the design space. So there's really good feedback using this tool. The RSM distance chart, what we're looking for here is that if I was to click on the stepwise regression, and it automatically associates what I click at the top to the chart beneath, that the blue line is the real set of data and the orange line is the virtual, the response surface, and the lines should overlay on top of each other, and we can see that the stepwise regression is a much more constant overlaying than any of the other 3. So once we've been able to do that and we can establish which ones are best, there's a number of things that we can do to our response surface. The first thing that we can do is that we can then try and run an optimization. We just go back into the workflow, we can select the response surface that we believe is the best and tell it to run 100% of the designs off that response surface, and then we can click the run button. Oh, but before I do that, sorry, I can select my response surface that is the best. I can also apply a strategy. A pilot is our multi-strategy algorithm that's very simple to use. We just set, not 2000, but we just set the number of designs that we want to run, and we don't even have to set a design of experiments or a starting point for the optimization, and then we can click the run button and we can run an optimization. So by loading up this test data, we've been able to train a response surface over the top very quickly and then be able to run a virtual optimization, not generating new real data points from a CAE tool or testbed, but generating them over these response surfaces. So you can see how quickly the designs are being generated. So they're very fast. And then once that's done, we can go into our design table and we can see that down the bottom it's generated these virtual designs that should hopefully have optimized our value of max C. So let's put those into a new table, and then we could plot a history chart of our objective, and we can see how modeFRONTIER has managed to increase the value of C. So that's the first thing that we can do. Another thing that we can do inside modeFRONTIER is we can take our response surface, we can export it. So we can export this in a number of ways. We can export it as an Excel workbook, which means that you can put that into another environment. If you want it into Excel, I can open up Excel directly from modeFRONTIER. Okay. So here it is, and now we get the response surface inside Excel, and we can interrogate that those response surfaces as well from that environment. Another way of exporting is that we could export it to a proprietary modeFRONTIER format called an RSM. Once we've exported that, that's done very quickly, then I can even build the response surface back onto the modeFRONTIER workflow and run it in a slightly different way than I did before. So we've got a response surface node. I can go and find that response surface file that I've exported. I can interrogate that response surface. It will find what inputs there are inside that response surface. I can drag out the outputs that are inside, and very quickly I could build up the same workflow and start optimizing for my C profile, but interrogating this response surface. Okay. So I think we're coming quite close to the end of what we can do. I think there's just one more thing that I wish to show you, if you bear with me, and that's this final node, which is called the RSM trainer node. Now, if all of that and the speed in which I was able to do all of that work before wasn't quick enough, and you don't want to go through a manual process, modeFRONTIER has a automatic way of doing this training as well, by using the modeFRONTIER workflow, so that the whole training of the response surface becomes an optimization problem in itself, especially when you're starting to look at some of the parameters that you can use to tweak and to tune your optimization. In this case, I'm just going to start from a different workflow. I don't think it was that one. I think it was that one. So I can drag on this RSM trainer node. Then in a similar way I can set what my training set is. So I can click this table here, as I can import it from a number of different locations, but I can import it directly from modeFRONTIER inside my design space. And I've got my training data. I can remove particular variables if I don't need them. Sorry, not from here. I can remove them from here if I don't need them. And I can modify my data and apply that into this node. I can ask a number of different response surfaces that I can get modeFRONTIER to try. In this case, I'll just select a polynomial SVD. We can tell it to validate using a table, and similar to the training set, I can go and select from the design space my training set, and I can apply those in here. I can also apply a RSM performance index, so if I wanted to maximize my R squared so that it tries and gets as close to 1 as possible, I can, and then I could tell it to maximize that value. Now, once that's all set up, I can then click on this parameter chooser. It will go into that data, and it will give me some values that we can change. So in this case, I could get modeFRONTIER to change the polynomial degree to step through the different degrees. And then for the outputs, I can extract a few different things. I could get it to extract the best RSM that it's trained, and also some error values. So I could get it to report back the error into modeFRONTIER. And even then, once we've extracted the RSM, we can actually get it to write back to the design space that appears into the design space, and there is a modeFRONTIER design space node. And once it's trained these response surfaces, it's found the best one, we can get it to then write back here into the design space node. So I won't run that now. I think I've probably spoken enough. I hope that has been of interest to you. If there are any questions, please do write them down now. Please don't feel embarrassed to write. I'm happy to answer any of those questions. Thank you very much.